All right, so I'm happy to give this talk today, and the topic is addressing the most wanted in digital intervention research, factorial experiments with Bayesian sequential adaptive designs. Okay, I'm gonna have to do some surgery in this title, because first of all, most wanted is, according to me, sort of right now, and I reserve the right to change my mind at a later date. The digital intervention part, it's gonna be mostly about behavior interventions, but I guess it sort of fits into other intervention thinking as well. And it's going to be quite shaped by my research in alcohol and tobacco and smoking digital intervention research. Also, a lot of this will actually apply generally to research in any sort of field. So there should be something in here for everyone. This Bayesian sequential adaptive design stuff is sometimes referred to as Bayesian group sequential designs and so on. So there's different names for this. And to be honest, this presentation is secretly an intervention to make you Bayesian. So just know that before you start. There's no informed consent form to sign or anything. If you're not convinced about the Bayesian perspective after this, you might just be upset. So be prepared for that as well. You just might be upset after this presentation. So with all that sort of entropy in the title, nobody should be surprised about what I'm going to talk about here. And there should be something in here for everyone. So my name is Marcus Benson. I'm a senior lecturer in experimental social medicine and public health at Linköping University. I have a background in data analysis, but my research mainly now is on digital behavior intervention research. I care a lot about how we evaluate these interventions, the methodology behind it, and how we look at effects and how we interpret effects. And that's why a lot of the discussion here today is going to be surrounded around effects, okay? So this is my most wanted. This is the hit list. This is what we want to get rid of. The first cluster, there's going to be two clusters. The first one is easily fixed. We can fix that straight away. I have the solution for you here today. We're going to be done with it. It's dichotomization of evidence. That is thinking about evidence as a true and full state, as if there exists an effect and there doesn't exist an effect. That kind of thinking we should get rid of. Null hypothesis testing goes hand in hand with that. We need to get rid of that. The voodoo of power calculations. So I was going to say here that don't come to me anymore and ask me to do power calculations, but I don't want to say that. Please do come to me and ask me to do power calculations, and we'll have a discussion about why it's a bad idea. So please do. And then the idea of incomplete experiments, and I'll show you what I mean by that. Those are easy fixes, applies generally to scientific research, but I think they apply very much to what we try to do with behavior interventions. The other cluster of issues is a little bit more complex, and I don't really have any ready-made fixed solutions for it, but I think they're important enough that we should acknowledge them. One is the data on effects of ingredients inside the pill, and I'll tell you what I mean by that soon. A move away, so I want to move away from calling it mHealth, eHealth, digital interventions. I'll tell you why I think that's sort of limiting us. And then blinding of participants and addressing other research participation effects. I'm going to have a talk next year in March about research participation effects generally, but I think blinding of participants, it's such a big issue in digital interventions that we really need to sort of put that up high on the priority list to sort of sort out. And I'll tell you why I think that is the case. So this is sort of the agenda. This is what we're going to solve today. Well, I'm not going to solve anything because most of the work has been done already. So I'm just going to tell you how to fix most of the stuff, okay? Those of you who know me know that this first part here with the dichotomization of evidence is, it gets my blood pumping to the degree where I need to sometimes just take a step back and take a pause because it gets me angry. But there are easy fixes and I'll show you how, okay? I also promised not to have any equations. So there will be no equations in my slides today. There will be figures and plots and diagrams, because I think that figures, plots, and diagrams actually tell you the essence of what the equations are trying to communicate, right? And this is one of them. And this is incredibly powerful. Now, a distribution, we need to know what a distribution is to be able to understand my presentation here today. A distribution tells us something about our uncertainty. It's incredibly powerful. I mean, just think about it. It's a way of communicating to others your uncertainty about a phenomenon. So what do I mean by that? Well, let's say we have this silly experiment. I'm going to pick a random person off the street and you tell me how tall they are. And you go, well, that's impossible. I mean, I don't know how tall they are. It's a random person. Well, that's true, but you do know something about the experiment. You do know that they're unlikely to be 5 meters tall. You do know that they're unlikely to be 2 centimeters tall. You have an idea about the general height of people in Sweden. So you could tell me, well, I don't know exactly how tall the person is going to be, but I'm going to guess that they're going to be average height of Sweden. I don't know what that is, 165, 70, doesn't really matter. So I think that on average, the height is going to be here. And then some people are going to be shorter and some people are going to be taller, right? So you don't have to tell me, I don't know. You can actually communicate to me your uncertainty about this random person I'm going to pick off the street. Makes sense, right? And for me, this is incredible. I mean, just think about uncertainty in terms of things you don't know the value of, but you can still communicate to me your degree of uncertainty and how you shape your uncertainty. That's super cool. There's other ways you could shape your uncertainty. I mean, you could just say, I think all heights are equally likely. So you could just have a flat line. Oops, I need a different pointer here. My mouse is... All right, never mind. No, because then I can't see. Ah, here we go. So you could have just a flat uncertainty here. That just tells you, you're telling me all heights are equally likely. Okay, I don't know. I don't know who you're going to pick, so all heights are equally likely. Perhaps you have something else where you believe that this could be uncertainty about high school students drinking. So you think most people drink 0, but some people drink more. And so you shape your uncertainty this way. And what's really cool about this is that when we think about scientific discovery and research, we identify some phenomena that we want to study, and we have some degree of uncertainty about this phenomena. So if we went to a different planet, you didn't see the inhabitants on this planet, and I asked you, okay, I'm going to pick a random alien, and you tell me how tall they are. Then you go, well, I can't really use this normal, well-defined distribution over here. I'm going to use this flat one. Any height is possible. I haven't seen anyone here yet, so I have no idea. Then I pick a random alien and I tell you, it turns out this alien was 30 centimeters tall. Okay, now you reshape. Now you don't think it's flat anymore. So you reshape your uncertainty into another sort of uncertainty, another distribution. And this is really nice. This is what scientific discovery is about. You have some phenomena you're uncertain about. You go out and you collect data. You come back to your office and you update your uncertainties. Now I believe this because I've seen some data. That's really cool. And if you have this nice warm feeling inside of you, like this is great, this is why I went into research, this is what I want to be thinking about, uncertainties, that's great. Keep that inside, hide it somewhere safe, because you're going to need it later on. It's going to get a bit cold on the next few slides here. So keep that nice warm feeling inside about discovery. Because we've sort of got waylaid in the middle of the 1900s, 20th century, I mean, into thinking that there's another way of doing scientific research, this dichotomization or null hypothesis testing. Okay, so I'm going to give you a refresher on this because sometimes people forget what null hypothesis testing is. First of all, you conducted a randomized control trial to investigate an intervention. You collected a data set, which we will now call D. So capital D is your Excel sheet. It has all the baseline data, all the follow-up data and everything. That's your capital D. And now you want to know something about the effect of the intervention. And we call that effect B, capital B. All right. And that capital B is sort of elusive to us, but we want to know something about it. So the null hypothesis framework says something like this. You use your Excel sheet to calculate an effect estimate B star, an odds ratio, or whatever you're studying. It depends on what the estimate will be. Let's call it an odds ratio. That's not the capital B, the population effect, but it's like an estimate of it. Why is it an estimate? Well, if you wanted to get to the true population effect, you'd probably have to include everybody in the population, every university student in the world would have to be in your population, and you would have to measure everything perfectly. And that's why I say it's elusive. You can't get to it. But you could get an estimate, and we call that B star. This doesn't qualify as equations, by the way, because there's no equal signs and there's no sort of X and Y here. So these are not equations. Now, I think most of you agree that if we redid the experiment, we would get a different B star, right? If I ask you to flip a coin 5 times, it's going to be a little bit different every time, right? So you're going to have a sort of a different outcome every time. So every time you redo your experiment, you get a different odds ratio. That's natural because you have a different sample the next time and you get a little bit different B star, that's fine. But what if I told you that, well, I can give you some information about these B stars even before you collect them. Just like I know that people's heights in Sweden have a distribution, these B stars will have a distribution. And they will be normally distributed. And the mean of that distribution, the center, is going to be B, the population effect, the one elusive effect you want, right? So just like you pick a bunch of people off the street, you measure how tall they are, they're going to be sort of unequally tall, but they're all going to be sort of centered and distributed around this mean average height in Sweden, right? And that center of that distribution is the elusive B that we want to get to. I can't see all of your faces, but none of the faces I can see are in disbelief and sort of not understanding what I'm saying. So I'm using you guys as a reference here that everybody's getting it, okay? So the true effect is B, that's the mean. Now, the null hypothesis says, what if B was exactly 0? So let's assume a world, and we go into this world assuming that B is 0. That there's 0 effect on my intervention, exactly 0. How likely is it that I would have collected the data that I did collect? So let's say it's like this. You go to Florida, you see a polar bear on the street, and you question the fact I might not actually be in Florida anymore, right? So we enter this hypothetical world that B is 0, and then we see some very odd data, like an odds ratio of 2.5. That seems incredibly unlikely that I would get a B star that is 2.5 if the true value was 0. That's like saying the average height in Sweden is 170 centimeters, and I just saw a guy that is 5 meters tall. And if that's the case, if it's so extreme, the data, then we reject this world. We say it cannot possibly be true that B is equal to 0. So we reject it. And then we reject the null hypothesis. And we say that the effect that we are measuring is distinguishable from 0, okay? I don't like this. I don't like this at all. I just spent a lot of time describing it. It's because I really want you to understand what it is, what's going on. I don't like this for several reasons. One, how do you redo your experiment? So we're hypothetically thinking that you can redo your experiment many times. That doesn't always apply, okay? Also, I don't really care if my effect is 0. Like you're asking the question if the effect is exactly 0, and nothing has a 0 effect. Everything has an effect. So I'm going to show you where this goes wrong, okay? And then I'm going to show you how to fix it. This is a trial we did a few years back on a electronic screening and brief alcohol intervention. So what goes on here is that you give a person a series of questions, somewhere between 10 and 12 or 20 questions about their alcohol habits, and they reply to the questions, and then they get some feedback and advice on how to change their behavior if that's necessary, if they drink too much. It's a very sort of simple one-session intervention, but it's a sort of been researched quite a lot in this community, in the alcohol brief intervention community. So that's basically what we got here. Doesn't really matter how that intervention was designed. All I care about is this table. This was the output from the trial. So what we saw was we had a population of about 900 people respond, a little bit more than 900 people in the trial. And we got a p-value of 0.13. Most people have been taught that if you have a p-value of 0.13, then you cannot discuss the effect you just measured. It means that we cannot distinguish the effect from 0. And so we are in no man's land. We don't know if it's 0. We don't know if it's not 0. And so we can't really discuss the effect of our intervention. Okay? That's bad. So what we did was we identified 3 outliers in the data sets. They reported drinking more than 1,000 grams per week, which is not impossible, but it's extremely high. So we assumed that these guys were lying or somehow data entry error. So we removed 3 data points from this data set of 900, and then we got a significant result. I went further and I found the one outlier that was extreme. That person drank 1,524 grams per week. I removed that person, that only one person, and then the p-value was 0.04, which is significant. I feel incredibly uneasy making policy decisions about does this intervention have an effect or not of a big trial when one person can move the p-value from 0.13 to 0.04. This is not scientific discovery in my mind. This is not how we should be thinking about developing new digital interventions. I'll show you the solution to this later. We'll revisit this example from the Bayesian perspective, but I think this stuff gives me nightmares. Like, how many trials have you read where the p-value has been 0.12, 0.13, 0.20? And I could probably identify one person in that data set that we need to remove to give you significant value. Yeah, nightmares. Okay. Another problem with p-values is that people don't get them. People don't understand them. And they are misinterpreted all the time. This paper got a lot of criticism from data analysts around the world. It was published in the, I don't remember if it was May or June. It was during the sort of major COVID sort of hysteria during the spring. And it was published in the New England Journal of Medicine. It's the best of the best, right? Impact factor is 70 or something, the best of the best. They have statistical editors on their board and they know how to do analyses properly. So basically this was a trial of the HIV vaccine or HIV treatment and if it helped COVID or not. And they found, and this is what they wrote, that the treatment was not associated with a difference from standard care in time to clinical improvement, with a hazard ratio of 1.31 and a confidence interval of 0.95 to 180. So because the hazard ratio was 1, a hazard ratio of 1 was included in the confidence interval, it was not statistically significant. And then they drew the conclusion that it was not associated, that there's no effect. This is not true. All you did was reject the null hypothesis. That does not mean that there's no treatment, that there's no effect. And people went nuts and went, this is the New England Journal of Medicine. You cannot write this as in an abstract. This is insane. Also, while sure, you cannot exclude the null hypothesis, you cannot exclude the fact that the intervention might not have an effect. But the upper bound of the confidence interval is 1.8. It's a massive effect. You can't exclude that one either. If you're dying of COVID-19, I take the treatment. I don't mind. I mean, it's not significant. I don't mind. I mean, if the doctor came in to me and said, Marcus, I'm sorry, but you're dying of COVID. I do have this treatment, but it's not statistically significant, so I'm not going to administer it to you. I'd be crazy. I want this, right? And there was also a long discussion about if the New England Journal of Medicine actually was, if they were sort of guilty of crime here, because there were reports that some doctors were stopping treatment because of this article, and people died because of it, right? This is a big issue. Okay, so those are good reasons why dichotomization of evidence and p-values should not be around. So let me go to the voodoo of the predefined sample size. I can tell you right now, although many people might disagree with me, you cannot possibly know how many participants you need to recruit for an experiment. It's a random number. You cannot know beforehand. It's impossible. Now, I've seen a lot of funny power calculations throughout my career, and people sort of manipulate, well, what if we increase Cohen's D from 0.3.035? That means we need to recruit 50 people less, and that looks better in the ethics. Okay, yeah, sure. That's great. That's a fine way of sort of convincing people that you need few people in your trial, but that doesn't help you to actually run your trial. This stuff is very interesting. So this is a trial that we did. It was not meant to actually test this hypothesis, but it sort of showed the weirdness of power calculations. So we were testing in a trial, we randomized people to two arms. In one arm, they received a public health message about alcohol, violence, and cancer, sort of explaining the risks involved. In the other arm, they also got information about alcohol, violence, and cancer, but we worded the text message as the alcohol industry would. That is, downplaying the complexities, making it seem like, well, there is some connection, but it's quite hard, and sort of responsible drinking is good, and so on. And at the end of the text message, we had a link which you could press to get more information. And the only thing we wanted to know was, do people who get the industry arm information, are they sort of numbed out? Do they were concerned about drinking, but then we tell them, well, it's complex and maybe you shouldn't be that worried and so on. So maybe they're less likely to press the link. They're happy with the information they got. Interim analyses after 150 participants. It turned out the participants in the public health arm were far more likely to press the link. The odds ratio was super high, 2.26. P-value 0.015, which we would sort of call quite strongly statistically significant. And me and my co-author Jim, we got all excited. Oh my God, the number, we had like 10 trials in our head just based on this going, now we can test this, now we can test this. We went nuts. We thought it was so cool. And it got me thinking, well, what if we had stopped the trial earlier? So this was after 150 participants. What would our results have looked like if we stopped after 10? 20, 30, 50, 100, what would our results have been? So I plotted this, and it looks like this. So the top one is the odds ratio we would have gotten had we stopped early at different participants. So here would have been 2 participants and 3, 4, 5, 6, 10. Here's 50 participants. Had we stopped, then the odds ratio had been here for 50 participants. As you can see in the beginning, it's quite wild. Like when you have few participants, the odds ratio is going to bounce quite a bit. The p-value, likewise underneath, the p-value is obviously not significant at the beginning. It goes a bit wild. And then after 50 participants, it sort of settles down. You see the p-value creeping down. And at this point, it actually crosses the significance line. So this is the 0.05 significance line here. And after 150 participants, it was statistically significant. So that's what we saw, right? This is when we did our interim analysis. So this is just a nice way of seeing what would have happened if we stopped the trial at different points of time. Okay, but we didn't stop the recruitment here. We actually did continue recruitment. No, before I get into that, just take a second to think about the number of trials you read where they said, we had 150 participants, we found an odds ratio of 2, this is great news, we have an effective intervention. Grant application, I've seen many grant applications, I've seen many ethics applications, I've seen many protocols that say we're going to recruit 150 participants to find an odds ratio of 2. You see it all the time. I read one the other day, right? It's not unheard of. Actually, some people think 150 participants is quite a lot and sort of use less. And then the next slide gives you nightmares. Because once we had recruited 560 participants, the p-value just went completely insignificant. Okay, that's sort of scary. The odds ratio went down. P-value just went insignificant after 560 participants. The odds ratio was 1.14, the p-value 0.43. So now you have to start thinking about, oh my God, all of those trials I read with 150 participants, what would have happened if they continued recruitment, right? When I saw this the first time, I was in disbelief. I was like, oh my God, this is terrible. I mean, when we say that we have evidence-based medicine, and we say we have this treatment, it's useful because it's statistically significant. We tested it on 100 people. Yeah, but what if you had more, right? So what I'm saying here is predefining sample sizes is voodoo. There's no way you can know. You can do it. It's fun. It's a nice sort of Saturday evening activity doing power calculations, but it's not great for science, right? So this study that we did was a study of what happens in control groups. So we wanted to know something about control groups. So often we use control groups in behavior interventions where we say, oh, go to this website or go to this platform, and we give them some brief information about health. And we wanted to know if that small information changed the way that people engage with extra sort of other material. So in this case, I don't care about statistical significance. I care about the distribution of the odds ratio. I want to know this because I want to use it in a bigger mathematical model. So experiments like these can be useful and are extremely useful, despite the fact that the p-value might not be significant. Okay. I apologize for any future sort of nightmares you might have about this, but this is concerning. But I'll solve it now. We'll solve it now. So remember when you conducted an RCT and I told you that you collected the data set D. D is your big Excel sheet. It's got your baseline values, your follow-up data and all of that, right? And you want to know about the effect of the intervention. Remember that nice warm feeling you had, maybe you had on my third slide when I told you about distributions and scientific discovery and research in general? Bring it out now, because now it's time to blossom into that again, okay? Bayes and Laplace basically solved this 100 years before Fisher got his fingers into statistical significance. So we've known about this for a long time. Well, there's two reasons why it hasn't really been deployed big time. One is political. In the middle, sort of, there was a movement against Bayesian statistics. It wasn't actually called Bayesian statistics back then. It was just called statistics because that was what everyone was doing. But the sort of null hypothesis testing and p-values was more politically correct in certain settings, and they got pushed out. The other one is that if you want to do something sophisticated with Bayesian statistics, you really need computing power. And it wasn't really until sort of 1995, 2000s, where we got the computers that were good enough to really do really cool big models in the Bayesian framework. So the computers that we have today has really helped us to do this. And there are several other reasons, but what I'll show you now is that when you think of terms as Bayesian, everything becomes so simple. Because what do you know about B before you start your experiment? Well, I can tell you one thing. If we're evaluating a text message intervention for smoking cessation, I find it very unlikely that everybody will quit in the intervention arm. I've seen enough interventions to know that maybe around 15 to 20 to 25% will quit, not all of them. So I know something about the effect size already before I do the experiment. So that's what I told you on the third slide. You have some phenomena that you want to study and you know something about it before you start. Now go out in the wild and collect your data. Get your Excel sheet out, start filling it out with data that you see and observe in the wild. And then come back home and update your knowledge about B, given the data. So all we're doing is shaping the distributions in ways that are meaningful to us. So the output of a Bayesian analysis is a distribution. It's not a point value, it's not an exact value, it's a distribution over effects. And what can we use this for? Well, we can use it to answer the questions that everybody is asking, but you've sort of been told that you can't really answer. You can ask, what is the probability that B is greater than 0? That is, what's the probability that my intervention had an effect? That's the question. I think every single researcher I've ever met wants to know the answer to that question. I've never heard a person say, I would like to know what the probability is that I collected the data I collected, given that in an assumed world where B is equal 0. I've never heard anyone say that. Everybody wants to know what's the probability that my intervention has an effect. You can also go further. You can say, well, what's the probability that my intervention's effect is greater than 1.5? What's the probability that the intervention effect is between minus 0.1 and 0.1? You can do all of these calculations if you want to, and you can really shape your uncertainty about this phenomena that you want to study. And it's incredibly powerful because you can go as complex as you like with your models and your thinking and your trial design, but you will always end up in this. The analysis is always the same. What did you know before you started the trial? What does your data tell you? What do you know today? That's fantastic. You can collect one data point if you want to. That's fine. You just shape your uncertainty after that data point. So I'll show you examples of this and what it might look like in a paper, because it's actually publishable. We've done it several times. You can publish Bayesian analyses. You don't have to publish p-values. The top table here is the one I showed you earlier, where we removed a few outliers and the p-value got significant when we removed outliers. The bottom one is the same sort of analysis, but from a Bayesian perspective. So we have our people here that have been in the trial. It's their consumption here, exactly the same. But rather than having these point estimates of saying a specific incident rate ratio and a specific p-value, we ask questions like, what's the probability that an incident rate ratio is less than 1? So for those of you who haven't worked with this before, just think of this that if it's less than 1, there's an effect, okay? The probability was 93.6%. That's quite useful information. What's the probability that the incident rate ratio was 0.96? Well, the probability was 71%. So a lower incident rate ratio means that the intervention had a greater effect. So lower is better. In fact, you can show them in the paper the entire distribution like this. So this is the distribution over the different effects. Everything below 1 means that there's an effect. And so if you had a mean value there at 1, or if you drew a line at 1, you would see how much of the distribution lies to the left of 1, and therefore you see how much probability there is that you have an effect. So when the student healthcare center comes to me and says, well, we're thinking about implementing this in all student healthcare centers in Sweden. Should we do that? Well, no, the p-value is not significant. So no, you shouldn't. There's no effect. Well, you can't say that there's no effect, but it's not distinguishable from null, so I wouldn't recommend it. That's bad advice. The probability that there is an effect is 93.6%. That's pretty high. And we're talking about a single questionnaire. I'm not talking about open heart surgery. I'm talking about a single questionnaire that we could offer to every single student, and we could reach a lot of people with this. The effect size is going to be small, but on a population level, you might have a massive effect, right? And also, if you're thinking that 93.6% or 71.5% isn't sort of strong enough for you, that's great. We should gamble. I mean, I'll take those odds any day. If you want to flip a coin and I'll win 93.6% of the time, I'll take that bet any day, right? So this is how we should be thinking. Like ideally, we want to show the distributions. Sometimes journals want you to give an estimate or a table, and then you can do that by just saying different probability cutoffs that make sense to you clinically. Because we're in the world of B, the effect, not in the world of the data. Okay, I hope a few light bulbs have gone on, right? Let me show just another example. This is a smoking cessation intervention among high school students in Sweden. And we did Bayesian analyses as well as p-value analyses. I just want to show you what it might look like in a paper. So we don't have to go through the details, but you see the distributions there. We plot them. You can look at the distribution and you see how much mass is to the right or to the left of 1. And it gives you immediately an idea of the probabilities of effect here. If you want to look at the table, then you can see some of these p-values are not significant, but honestly, who cares? All those p-values tell you is that you cannot reject a hypothetical world where the effect is exactly 1. And it's a very uninteresting question. Astonishingly uninteresting questions, given that all interventions have an effect, some kind of effect. Okay. We're doing good on time here, so I feel like we'll be able to have a good discussion. Okay. Have I solved anything yet? Yes, we've solved the first two, dichotomization of evidence and null hypothesis testing, right? I haven't solved anything. Bayes and Laplace solved this a long time ago. And to be honest, there's absolutely no reason to do dichotomization of evidence or null hypothesis testing. We have the tools available to us to do it in a much better fashion. And I'll also solve the next two, the voodoo power calculations and incomplete experiments. And some of you should get super excited about this. Because in Bayes land, when we're in Bayes land, each participant is an experiment, okay? I take one participant into my trial, I run an experiment. Then I take the next one and I run an experiment. I take the next one, I run an experiment. Every participant is an experiment. And each time you collect a data point, you're allowed to update your knowledge about the phenomena that you're trying to study. So in the left plot there, you see I had this belief that my text message intervention is unlikely to be effective. Most of the effect is around 0. So that's what I thought before I started my trial. there's some probability that it will have an effect that is greater than 0, but I'm thinking that it's not going to be effective. Then I enroll a few people. Let's say that each blue dot there is 10 people. I enroll 10 people in my study, and then I recalculate my distribution. So, well, it turns out that it has some effect. So I reshape the distribution now. I collect 10 more and I reshape it a bit more, and 10 more and I reshape it a bit more, and 10 more and I reshape it a bit more. And I can go on as long as I like. I don't pre-specify how many people I want. I just sort of collect data and reshape my uncertainty in a way that's meaningful to me. And what's meaningful to me? Well, you need to put that in your trial protocol. You need to say upfront what's meaningful to you. So in the trial protocol, you would put something like this. If we see a probability of positive effect that is greater than 97%, then we stop the trial, okay? I'm going to define a successful trial as the probability of effect is greater than 97%. So that's the target I want to hit. You could also say, well, if it turns out that people start smoking more when they have the intervention, then I want to stop as well. That it means that my intervention is harmful, so I want to have a criteria for that as well, and I stop if the probability of harm is greater than 80%. And you can also have a criteria for futility. If I see that the probability of effect is very, very small, or the probability of a small effect is higher, so you have a tight range around 0, and the probability that your effect is within this tight range, it turns out that this might not be worth doing. We can just stop the experiment. There's not going to be an effect here. This helps you to avoid stopping early because you're skeptical to start with. You start out with skepticism, and that means that you're not going to be persuaded by small sample sizes. And it avoids recruiting too many participants, and also avoids recruiting participants to harmful interventions. So I have an example now of a trial. We pre-specified 2,000 people. We had all the results we wanted after 1,000 people. But since we pre-specified 2,000, we have to keep going, right? It's insane. So doing this voodoo of power calculations is going to get you into trouble. It's going to get you into a lot of trouble, because I've also seen trials that quit after they had the sample size that they pre-specified, and they were tending towards to find an effect, and then they say, no, sorry, we specified 500 people, so we stop here, and we don't have a significant effect. And then you usually see this sort of acrobatics in the English language in the discussion. Well, we didn't have enough power to detect the effect, but if we had more people, we might have seen this effect and this and this and this. When in fact, they should just have continued recruitment given some targets. And because we're in Bayes land, we can do this per participant. You can recalculate these probabilities every time you get a new data point. So you will stop precisely when you have the results you were looking for, or when you've shaped the uncertainties in ways that is important to you. Incredibly powerful. Okay. Remember this horrific picture that gave me nightmares when we stopped after 150 participants with significant results? Looked at it and went, wow, this is super cool. This is what we want to do. And then it turns out when we recruited more, we got disappointed. This is heartbreaking for researchers. This is like, oh my God, I feel sorry for myself. I feel sorry for myself. But we can, if we go Bayes land, if we go Bayesian here and we do sort of the Bayesian, I didn't actually name the procedure I just mentioned. The procedure I just mentioned is what's in the title, the Bayesian sequential adaptive design stuff. That's what I just talked about. If we go Bayesian, then we would have something like this. The top one is the Bayesian estimates of the odds ratios. Don't worry too much about that one. This middle plot, though, it shows the probability of success. So we would have stopped our trial if we had reached our target probability of success. And as you can see, we were never close. The horizontal line there shows us where we would have stopped the trial for success. And we wouldn't have stopped after 150 participants. It was never close. The bottom one shows futility, that if we believe that the odds ratio is in a very tight range around 1, we don't really think that this experiment is worth continuing. And as you can see, we're trending up towards that. So if I had to predict, I'm expecting us to sort of stop this experiment due to futility. We don't think that the effect sizes are in a range that is sort of clinically significant for us in this context. So using this Bayesian sequential updating and incorporating that in your RCT trial design helps you to not make stupid decisions after 150 participants like we did. And it also helps you to sort of define what you want from your experiment and then continue observing the sort of experiment and observing the world around you until you've shaped your uncertainties in ways that are important to you. Don't worry about the p-value. What do you want to get out of your experiment? That's what you should be asking. So I'm just going to say that those are solved now. Like, that's brushing everything under the carpet, but I'm just saying, put Bayes and Laplace on this and you're done. Like, you don't need to worry about these issues anymore. They're solved. I should say though, obviously this implies that you have the data after each participant, and that might not always be possible. You know, you have 20 clinics collecting data for you. You're not going to be able to run around to those and collect all the data every day and say, oh, I need to do my Bayesian updating because Marcus told me I could do this. So it's super cool. I want to do this now. Obviously, that's not always going to work. But in digital interventions, a lot of the time we do get the data continuously. Sort of they have an app and they might respond to questionnaires in the app or something. And then you actually have the data, so you can do this. I also should say, by the way, that this is not sort of just me thinking that this is a good idea. There's a whole sort of research community thinking that all that I just said is a good idea, right? So it's not just me coming up with wild ideas. Okay, now moving on to the more complex stuff that is actually quite hard to address, but I have some ideas of how to do it. We do sort of tend to call it M-health, E-health, digital, and so on, right? But in reality, that's just saying that we're dealing with white pills. So if I wrote a meta-analysis with the title, what is the effect of white pills on headache? People would go, you can't write that, that's ridiculous. But we do write meta-analyses of what's the effect of M-health on alcohol interventions, right? But that's just a mode of delivery. It doesn't really tell you that much about what you put inside the pill, right? And I care about what you put inside the pill, not so much the mode of delivery. Having said that, sometimes the mode of delivery is important. I mean, a pill versus a syringe and so on, right? And if I'm reading an intervention of a text message intervention, or a paper about a text message intervention, then I'm thinking in my head, well, this could be rolled out as a public health intervention. Most people have a cell phone, most people can receive text messages, so it's on a different scale. And I'm happy with smaller effects in those type of trials because I'm sort of thinking, well, we could sort of distribute this worldwide easily and so on. So it does matter, the mode of delivery. But of course, if I'm reading a paper about an intervention using Apple Watch, then I'm not thinking so much public health because an Apple Watch intervention is going to be very specialized among the people who own one and so on and so forth. So I'm not saying that the mode of delivery is unimportant. I'm just saying that it's not very informative of what you're trying to do with the individual. Now we have the behavior change technique taxonomy, which a lot of people are familiar with. And I think that's a great sort of step in the right direction of systemizing a language so that we can communicate to others what we put inside our interventions. I think that's good and I think it's useful. But meta-analyses that go backwards and say, well, we're doing a meta-analysis and then we're going to identify which BCTs they used to connect sort of effective BCTs or sort of trials with these BCTs are effective, so hence the BCTs must be effective and so on. That's a step in the right direction, but that's an incredibly confounded analysis. There's a lot going on and taking it that route is useful for hypothesis generating, but it doesn't really tell you the effect of the BCTs, to be honest. But it's useful. And what I'm looking for is experiments designed with the purpose of measuring the effects of the active ingredients in an unconfounded way. So you don't start off, you start off with the idea, we want to measure the effects of the components. Keep that in mind. I'm going to talk about blinding of participants, and then I'm going to find a solution for you that solves both of them, right? So one thing is, how do we figure out what the active ingredients are? And then we're going to look at blinding now, and then I'm going to tell you how to solve it. We do a tremendously poor job, I would say, in behavior intervention research to address research participation effects. In any behavior intervention, we should expect research participants to behave in ways that we don't want them to or expect them to. People are crazy. This is what happens when you sort of do research on people. I used to do research with just computers and simulated data. And they're so nice because they always do what you tell them. There's no error in a data number. It's fantastic. I generate a bunch of data, I do analyses, everybody behaves. If I need another 1 million data points, it takes 5 seconds. And that's not how medicine works. People are crazy, people do stupid things in trials. And I'll have a talk in March about research participation effects more generally and in depth. But one thing that really is a concern is blinding of participants in digital intervention trials. When you don't blind participants, you open up for a host of biases: social desirability, compensatory rivalry, waiting to change, positive promotion. So just as an example, we've seen studies that have shown that if somebody's told that they're in a waiting list control group, then they won't change their behavior at all. They would stay the way they are because they're waiting to change. They'll change when they get the intervention. That's not how we expect a control group to act, because we want a control group to replicate what people would have been like had they not been included in the trial. Positive promotion is a fun thing. You know, we evaluate if people like our interventions, and if people are happy with the intervention, we are happy. Sort of, yes, I thought it was really good. I would recommend it to a friend and so on. That's actually a problem. It feels weird saying that it's a problem if people like our interventions, but it is a problem because you could have people reporting less alcohol consumption, for instance, because they like the interventions and they think that people should have it. So they want to bias the research study in a way that makes the intervention more effective than it actually is. So if we don't blind participants to allocation, we're going to have issues. And this became very clear to me when we did a meta-analysis of alcohol interventions. If you haven't read meta-analyses before, then you probably haven't seen these types of figures, and you don't have to understand them because you only have to look at the colors. That's great about this. This red bar, can you see my mouse move here? Yeah, okay. This red bar here indicates that a strong majority of the trials included in this meta-analysis here did not use blinding. This red bar here, same thing. This is a different meta-analysis. They did not use blinding in most trials in this one. This one here is from a Cochrane review. This column here, all the red dots indicate that these trials did not use blinding, and it's a strong majority. And this is a big concern, I'd say, because these three meta-analyses are quite different. The one to the left is of purely text messaging interventions. This one here is among adult populations. It's digital interventions and CBT platforms and so on among adult populations. And the Cochrane review is quite general. But when you look at the system, so the synthesized results, effect sizes were quite similar. So you have this wide range of populations, wide range of interventions. The one thing they have in common is that they didn't blind participants, and we have sort of similar effect sizes. And you could argue that over the last sort of 20 years of digital intervention research, what we successfully measured was bias. No intervention effect at all. We've just measured this bias due to blinding. So I apologize in advance. That's quite a leap of a hypothesis leap, but it's potentially there, right? The one thing all these trials had in common was that they didn't blind people, and we see sort of similar effect sizes. That should be a red flag. So we need to start thinking about blinding participants in ways that that help against or protect against this. That's difficult. If you went into a trial of a text messaging intervention, you expect to get text messages. So you can't really say that you're not going to get text messages. If you don't get them, you know you're in the control group. That's like having a trial of surgery, right? You know you had surgery. It's ethically unsound to put people under general anesthesia and just wake them up and just say, yeah, you might have had surgery, or you might not have. We're not going to tell you because there's placebo effects, right? You don't do that, right? And it's just, so we have this problem, but it needs to be solved. And the old finance minister finance secretary in the US had a great quote. He said, just because a problem doesn't have a solution doesn't mean that it's not a problem, right? It's fine. You can say, well, we couldn't blind participants, but that doesn't mean that it's not a problem. It's still a problem. So here's the solution. Well, part of the solution. Part of both sort of the issues I raised here. A factorial design. So rather than estimating the effects of your entire intervention as a bundle, so rather than saying, I have this app and I want to test the effects of it, we break the app up into components and we contrast the components against each other, okay? So that's one step towards really digging into what components are effective. Now, if you were not familiar with factorial designs, you would go, oh my God, then I'm gonna need like 8 arms and I'm gonna need to recruit 800 more people than I expected and so on to get the proper power and so on. But a factorial design actually solves this for you. So you don't have to recruit more people than you would have normally. And of course, we don't know how many people you need to recruit because that's a random number. It looks like something like this, okay? This is a very basic factorial design. Component 1, component 2, component 3. There's 3 components in this app that I'm developing. Let's say that the first one is goal setting. The second one could be feedback. And the third one could be expressive writing. Those are the 3 components you believe you want to put inside your app and you want to test the effects of these components. Now, for each component, you're going to have to define a basic level and an advanced level, or a basic and enhanced level, okay? So 0 means that you get the basic version. So for goal setting, let's say that is a small text message that says, make sure you set goals for yourself and keep track of them. That's the basic version of goal setting. Well, if you have a 1, that means you get the advanced version. That means you get maybe a timeline that you can draw on. You get tips for how to set your goals and how to achieve them and so on. So we have a basic version of goal setting and an advanced version of goal setting. The same thing goes for the feedback and the expressive writing. Then you have 8 conditions. So you randomize participants to these 8 conditions. The first condition, you get the basic version of everything, okay? So you get the basic version of each component. The 8th condition gets the advanced version of each component. And the ones in between get sort of a mixture of those. So you covered all the cases here. What's great about this is that despite the fact that we have 8 conditions, you only need the same number of people that you would in a normal trial, because we're evaluating component by component. So if you look at component 1, then 4 of the conditions have received the basic one, and 4 of the conditions have received the advanced one. So you still have the full sample when you do the analysis for component 1. So that's very clever. What does this mean? Well, first of all, you're estimating the effects of the components themselves, not the entire intervention. And that's sort of what I want to get to. That's where I want to be. I want to be in a setting where I'm evaluating the components rather than the entire intervention. I want to know what's inside the white pill and what works. Also, you can do very cool stuff with mediators. Suddenly you can say, well, we have this mediating factor like self-efficacy or something. And then I could ask, well, how much does component 1 affect self-efficacy and then to the outcome and so on. So we can do much more detailed mediator analyses. And hopefully, if we design this properly, everybody will feel like they got something. So it will be consonant with signing up for a trial of an app because everybody got something. And this should be investigated, I think. I think after the trial, you would have to do qualitative interviews with people to check, what did you think about the app? And if they say, what do you mean? I didn't get anything. And they were in condition 1, then your blinding has failed, right? But this is a way of blinding people because in the informed consent, you would say, we're trying out different versions of an app and you're going to be randomized to one of them. So everybody feels like they got something, like they got a part of the intervention. But you would have to check to make sure that people in the lower conditions don't feel like they received nothing, because then blinding might have failed. Likewise, you want to make sure that people in, for instance, condition 8 and condition 7 aren't super, super happy with intervention compared to the others, because then you've also opened up an issue with people being more happy with what they receive might be more biased towards reporting positive results. Okay, there have been trials that have used factorial designs. This is one, Claire couldn't be here. She was supposed to be here and talk a little bit about her trial. So if I'm going to say a few negative things about her trial and she's not here to defend herself. So that's, yeah, I don't think she's joined. Anyway, this was a smartphone app to reduce excessive alcohol consumption, identifying the effectiveness of intervention components in a factorial randomized trial. They used, so here are the components. They had 5: normative feedback, cognitive bias retraining, identity change, action planning, and self-monitoring. And they had an intensive and a minimal version. You can see they have these two conditions. And they randomized 336 people to each one of those conditions, right? There were no significant so I put a caution here. They had an incredibly high attrition in this trial. So any results from this trial should be you should really think about that before you draw any conclusions on this. So that was a big issue of the trial. Another one was that they didn't use a Bayesian design. So they had a fixed sample size that they recruited to, which also created issues. So they should have really adopted the Bayesian design. But they did find two-way interactions. So that's also cool. The factorial design allows you to test two-way interactions. So it suggests that people that had normative feedback and cognitive bias retraining, they had a lower weekly alcohol consumption. So you see the combination of different components, you can measure the effect of that as well. Also, enhanced self-monitoring and feedback and action planning affected audit scores. Audit is like a questionnaire for alcohol habits. What is also interesting is that enhanced self-monitoring and feedback was used significantly more often and rated significantly more positive for helpfulness, satisfaction, and recommendation to others, which is what I've said before might be an issue. If somebody likes a component a lot, that might also mean that they are more positive to the intervention. And as you can see, self-monitoring actually stood out as something that might be effective, but people also liked it, unbalanced with the others. So that could be a problem. Anyway, these factorial designs exist, so you can read about them. This is a published one, it's done. You can read about the whole design and copy the design if you want to. So it's not unheard of, it's not something new. It's just that it's not used a lot. This one is from 2018, and there's only a handful, I would say, even if that, in alcohol intervention research that uses factorial designs, but they tell you so much more. Like if this study had been fully powered and they actually had lower attrition rates, it would be super, super useful to dig into the different components. So I think this is a great idea. But obviously, we want to do this the Bayesian way. We want to go into Baseland and use our factorial trials. So you do the exact same thing, but now you define criteria for effect, harm, and futility for each component, okay? So before I told you, you need to define criteria for your intervention as a whole, but now we do it for each component, and you recruit people to this trial. But once maybe you find after a while that component 3 is harmful. For some reason, component 3 makes people drink more. So we don't want to include that. We're fine. We're happy with what we learned about component 3. So we drop it. This also means that we can drop some of the conditions. So we can actually reduce the number of conditions we randomize to. So we can be very, very dynamic. We can start out with 5 components. We can identify components that seem futile and we just drop those. Components that are effective, fine, we know that now, remove that one, and then we can reduce the number of conditions, and we can speed up recruitment quite significantly. And I think this is one of the things about digital interventions in general. There's a need and a want for digital interventions. And so people use apps and stuff that's not available, or not evidence-based, I mean. They just use what's available. And the research field is a bit slow because it takes a while to run an RCT. It takes a while to recruit participants. It takes a while to do analyses. It takes a while to get funding. So anything that we can do to speed up the RCT part, to recruit people to the conditions that matter to us and that we can learn more quickly will be helpful, because then we can get out sort of effective interventions a lot sooner into the public. Perfect. We solved the first cluster of issues. Like, there's no real need we have the solutions for that. The second one is sort of, oh, by the way, I should mention, before I lead somebody down into a dark hole, I haven't actually tested this. This is completely untested. Don't go do this just because I said it was a good idea. We need to do some research if this is a good idea, and we need to do simulations in the computer to see if we actually get the sort of, what are the pitfalls and so on. This is completely untested. Although there's research on dropping arms and so on. So you could sort of combine this with that. But we're going to run a trial starting next year with this type of design. And so we'll learn more about this type of design as we go along. Anyway, the first cluster is done, solved. If you're sitting on data right now and you're thinking, what would have happened if we done a Bayesian analysis? What would have the outcome been? Would we look at things differently? Please contact me. We'll set something up. We'll do some analyses. We'll look at it. We have a special issue in JMIR where you can actually publish your results from already published papers. So if you already published your results, but you want to publish a Bayesian analysis of those data, then we have a special issue on JMIR where you can publish that. So we can get that done as well. So for sure, contact me if there's anything you would like to sort of look at again. And for this other part, I think it's worth discussing how we can solve those issues that I said, sort of blinding, looking at the components of the intervention. I'm not saying that my suggestion of factorial design is the best one. I know it's not the best one. I'm sure there are other ways of doing this better. At least it's sort of work in progress of getting somewhere closer to what we want to investigate. We want to know what works inside the interventions. We don't necessarily just want to know if an intervention as a bundle is effective.